Level set based topology optimization. What is topology optimization? Topology optimization is a mathematical approach or a technique in which it optimizes the material layout for a given set of constraints and to meet certain performance objectives. So this concept is initially started by Benso and Kikuchi for structural mechanics problems, but now it finds application in various fields, including fluids, acoustics, electromagnetics, optics, and so on. And what are the methods available to implement topology optimization? There are various methods, and the popular ones are density method, level set method, topological derivative method, phase field method, and so on. Now let's look at what is topology optimization is. Let's take a structural mechanics problem wherein you have a rectangular beam subjected to a tip load F. Okay, and now that you want the beam to be have a maximum stiffness, but you want to use less amount of material, say, and you want to use just 30% of the material uh, which will occupy this rectangular domain. So in that, if that is the situation, then where the material should be distributed or what should be the shape of the beam so that it will have the maximum stiffness, yet it will consume only a given percentage of material. So the solution can be obtained through topology optimization. Um, I just run this solver, and now as the solver runs, it it uh, it inserts material wherever it is required and it removes material where it is not required to achieve maximum stiffness. So the black represents the solid, and the gray that you can see on the periphery of the beams is the intermediate. So intermediate material, like it is a 50-50 material or a void, and the white represents where you don't need any materials. So by populating or by inserting materials in these places, you will just consume only 30% of the material, yet it will have maximum stiffness. And this animation is based on a 99-line MATLAB code written by Oli Segment. So topology optimization by level set methods. So this is another popular method which is presently used by researchers for topology optimization. Level set basically means a set of points where the function takes same value. So if, let's say, the function is x squared plus y squared equal to some constant, okay, so that will represent actually a cone, and if that x squared plus y squared equal to some numerical value, say 9 or 60, and then it represents a circle. So the major steps in topology optimization using level set is, first you need to um, decide, whether you're going to use a polynomial functions or radial basis functions for parameterizing the level set functions. And next you need to map the geometry. I mean, maybe it could be a series of circles. You need to map the series of circle geometry into the mechanical properties. So where you want the material, where you want the void, such a mapping has to be done. And it could be based on ersatz material method or exfil or conformal mesh. So these are the different techniques available for the mapping. And the third is optimization strategy. You need to decide on the optimization strategy. So how the shapes are going to evolve. So one approach is you can solve the Hamilton-Jacobi equation to convert from one particular shape to another particular shape. So this is commonly used. The other popular method is mathematical programming. So thereby you change the shape from A to B. So here you can see the rectangular one is the design domain, and at one particular instant during the optimization, the shape is something like this, and inside the level set, inner region of the level set is assigned as a material, and outer region is assigned as a void. So thereby uh, you can you can run this optimization and get a final shape of the material distribution. If suppose psi is the level set function, then here we assign when psi takes a positive value, we say that's a solid region, and when psi takes a negative value, it's represented as a void region. And the Hamilton-Jacobi equation is dou psi by dou t equal to minus v times mod del psi minus omega g, where minus v is the velocity of propagation, and g, the term, the constant term or the second term omega g, is for nucleation of new holes into the design domain. Okay, so what are the advantages of level set method compared to the density method? So suppose if you're using XFEM or conformal mapping based um, material mapping, then you will get rid of the pressure diffusion problem, uh, which is felt in density based methods. So there won't be any pressure diffusion, and the pressure obtained as a result of this optimization will be closer to the realistic value. The other one is it is accurate in predicting the interfaces. You can avoid the gray regions where you're not sure whether to have a that particular cell as a solid or as a void. So these are the disadvantages. And compared when it comes to the disadvantage, compared to density method, convergence level set method is slower. So that's one disadvantage. So here in this problem, again a cantilever problem is taken, but here we don't have we have the load at the center of the extreme end. So the red represents material and the blue represents voids. As the solver or as the optimizer runs, you get this the standard cantilever beam shape, which will have maximum stiffness and have particular percentage of material usage. So how to implement this level set method? So what are the steps involved in the numerical implementation? Okay, so this is one particular approach, and there are various methods. But let's look into this one. So first, you need to initialize the level sets. So you might be taking some polynomial function as the level set and distribute that within the design domain, and then take that information into your physics solver. So here in this case, people use COMSOL multiphysics for solving the physics. So that your physics could be a structural mechanics problem, or it could be a thermal problem. So for the distributed level set, you do a mapping between the material properties and the geometry, and then based on that, you solve your physics and obtain the objective value. If it is a structural mechanics problem, it is the stiffness, or if it is thermal problem, it is the thermal compliance. Evaluate the objective and evaluate the sensitivity, and then find out how far you are from the area constraint or the volume constraint. So evaluate these three and then pass these three informations into your uh, optimizer or the Hamilton-Jacobi solver. So here in this case, this Hamilton-Jacobi solver uh, solution is made using a MATLAB program. So MATLAB receives this objective function sensitivity and area difference, and based on that, it solves the Hamilton-Jacobi equation and gets the new level set distribution. And now you check for the optimization convergence. If there is no difference in the objective function value, then you can say that the problem is solved. If not, if you see a considerable difference in the objective function value, then uh, then the new shape will be passed on to this physics solver, where again the geometry mapping and solving the physics will be done for the new shape, and then the new sensitivity and new objective values and the area difference will be passed back to the MATLAB program, and this iteration will go on till you reach the shape convergence. And in the case of level set method, there is an additional step which is called reinitialization. So as the shapes um, convex or progress to the new shape, the level set, which is, let's say that you are having cone shapes. So as you propagate it, the slope of the cone may not be one. So sometimes it may become steeper, or it could become very slant. So if it deviates from a slope of one value, then it results in gray cells. So to avoid that, you need to do reinitialization, and so that is done by solving the Eikenol equations. So this is one additional step, which is a part of the levels of numerical implementation. So um, with this implementation, you can solve uh, your your physical problem. It could be structural mechanics or thermal problems. Thank you.